Alright, this video we're going to continue with some applications of L'Hopital's rule to limits that are undefined. So first of all, we're going to start with this example here, and we're going to try just plugging x equals to 1 directly into the equation, into this formula. So it turns out we're going to have 1 plus 2 minus 3, that's going to become 0. Now at the bottom we're going to have 1 plus 1 plus 5, that's 7, minus 7 is 0. Oops, we have an undefined value. So what we're going to do instead is we're going to differentiate the top and bottom. So we're going to apply L'Hopital's rule, and we're going to say, okay, so let's have 2x plus 2, and that's going to be divided by the derivative of the denominator, which is going to be 3x squared plus 2x plus 5. Now let's see what happens when we plug x equals to 1 in here. We're going to get 2 times 1, that's 2, plus 2 is 4. And in the denominator, we're going to get 3 plus 2, that's 5, that's 10, which means this is going to be about 0.4, I would argue. But essentially, that's what you're going to get. And it turns out that this is actually a very, very surprising result, because when you look at this function, you might think, well, if you get a result like this, maybe there's something going to infinity, maybe there's something that is just undefined. But if you differentiate the top and bottom, you get an expression that you can actually plug in the value of x into, and you get a very neat result for it. And if we actually go and plot this on Wolfram Alpha, and I like doing this for pretty much everything I do, is we're going to look at this function, and it turns out that at x equals to 1, which is about here, we're going to essentially get 0.4 as we calculated. So it's not going to be undefined after all, and that's a very, very neat result. Now we're going to look at an expression that is a little bit more challenging, but hopefully this is going to solidify your understanding of L'Hopital's rule and when it is appropriate to use it. So suppose you have something like this. You have n going to infinity, which means you're going to have a bunch of infinities here. So in the end we can just write infinity, then a bunch of infinities over here. Whoops, that's not defined, so obviously we can't work with that. Now let's try and differentiate this. Let's apply L'Hopital's rule once again. But we're going to differentiate the top and bottom. So we're going to get 3n squared plus 4n plus 3. And then differentiate the bottom. That's going to be 6n squared plus 8n plus 6. Now let's try and plug in infinity again. That's going to become infinity. That's going to become infinity. Oh, what happened here? It turns out that applying L'Hopital's rule is not working in this case. So does that mean that L'Hopital's rule doesn't work in general? Does that mean that it was just a fluke, that it worked for the previous examples we did? Because I very exclusively chose those examples to work for L'Hopital's rule. Was I tricking you into thinking there was a general rule that applies for any kind of problem like this? Well, it turns out that if we think about the actual implications of L'Hopital's rule, and I'm going to write this down here because it's a very, very important result. The limit as x approaches some value a of the function, some function say f of x divided by g of x. If you get something undefined, it's going to be the same as the limit x goes to a of f dash x of g prime x. So we're taking the derivatives. And if this doesn't work, well, these functions are different to this one. So who is not to say we can just forget about this side and then differentiate these two functions. So they're going to become new functions as well. And perhaps it's going to look like this: f double prime x, g double prime x. And it turns out that you can continue this process and it is always going to work. L'Hopital's rule works, and you can differentiate the top and bottom as many times as you want until you get an answer that is not undefined. And that's a very remarkable thing. And this blew my mind. When I first learned it, I honestly had no clue that you could differentiate this thing more than once, but you actually can. And I'm going to show you how you can do this right now. So we're going to go limit as n goes to infinity. We're going to differentiate top and bottom again. So that's going to be 6n plus 4. That's going to be 12n plus 8, okay? And then the next thing is going to be, well, if we plug in n equals infinity, that's clearly going to give us this thing again. Very ugly. So let's differentiate once more. Okay, so that becomes 6, that becomes 12. And it turns out that the limit of this whole function as n goes to infinity, which is seemingly undefined, is a value of 1 over 2, or just half. And that's a very, very amazing result. And it blows my mind. Every single time I do this, it blows my mind. And I hope it has blown your mind as well. And it is so useful because, and actually, I'm going to teach you a very, very nice shortcut. So let's say you have a very general function. So 2 polynomials. And then you have something like this. So let's say at the top you have x to the power of n plus, actually, let's make it x to the power of n minus 1 plus, and then let's say you have a bunch of numbers, a, b, plus, and so on, and that continues. And then at the bottom you have some other set of another polynomial. So you might have something like a2 x to the power of n plus b2 x to the power of n minus 1 plus, and so on. Now obviously for any point here where you put x equals to infinity, you're gonna get infinity over infinity, which is gonna be undefined. So what you can do instead is you can continue to differentiate each of these, but instead of actually caring about this, because you know that at some point all of these terms to the right, so basically if you cut it over here, all of these terms are gonna become 0 if you differentiate it more than n minus 1 times. And then all of these values over here are going to become 0 if you differentiate this expression more than n minus 1 times. So you're going to be left with just these two expressions. So you can differentiate as many times as you want. So you're going to have something like a times n x to the power of n minus 1. So that's the first time you differentiate, plus a bunch of stuff on the right hand side. And then this one is going to be a2 times n times x to n minus 1. Now obviously that's still going to give you something that is going to be infinity over infinity, so you can continue to differentiate that. And remember, because every other term here is going to become 0 eventually, we only care about the highest powers of those polynomials. So that means that this one is going to become a n, then n minus 1 by applying the chain rule, x n minus 2, and then plus a bunch of stuff that we don't care about. And then over here you're going to have a2 n minus 1. X to n minus 2, and you're gonna continue this process until you have essentially reduced this to a constant, and that's basically it. You're gonna find the limit of this function without actually having to go through the trouble of differentiating every single term in that polynomial, and that's a very, very neat trick. So hopefully this has given you a very good idea of what L'Hopital's rule can do, some of the properties of L'Hopital's rule, and the fact that you can differentiate top and bottom as many times as you want and it will still work. It will allow you to find a finite limit. And yeah, that's pretty much it. And in the next video we're going to be looking at some more interesting examples.